Hi, welcome back. In this video, we're going to define similar matrices, prove a property, and a couple of facts about similar matrices. So let's start with the definition. Suppose you have two square matrices of the same size, so they're both n by n. Then we say A prime is similar to the matrix A if A prime is equal to P inverse times A times P for some invertible square matrix P. So to prove that A prime is similar to A, you have to find an invertible matrix P and then show that A prime is equal to P inverse times A times P. So let's look at how this is related to linear transformations and matrices that represent linear transformations. So let's start with a n-dimensional vector space. So V has dimension n, and let's say we have two bases for V. B and B prime are two different bases for the same vector space. Then say we have a linear transformation T that goes from V to V, and suppose A prime is the matrix for T, but relative to the basis B prime. What does that look like? So here we've got V, and we've got T that goes from V to V, and so we're starting with a coordinate vector for V relative to the basis B prime, and so multiplication by A prime takes us to the coordinate vector relative to B prime of the image of V. So the transformation does the same thing as multiplication by the matrix A prime, but the vectors in the domain and in the range are all coordinate vectors relative to the basis B prime. All right, so let's suppose A is the matrix for the same linear transformation, but relative to the other basis B. So here's the same picture, but we're using the matrix A for the same linear transformation. It means that we're taking a coordinate vector relative to B for the same vector V, multiplying that by A, or doing T of it, and we're getting the coordinate vector relative to the basis B, the same basis, of the image of V. Now, remember, we know how to get transition matrices. So let's say P and P inverse are the transition matrices to go from B prime to B, or from B back to B prime, right? To transition from one basis to another. So let's say P is the transition matrix from the basis B prime to the basis B, and P inverse is the transition matrix from the basis B to the basis B prime. So now notice that we can compose transformations or matrix products. We can start with the coordinate vector relative to B prime of the vector V and just multiply by A prime, and that will take us to the coordinate vector relative to B prime of its image. So it'll be the coordinate vector relative to B prime of T of V. We can also go the long way around in that diagram. We can start with the coordinate vector relative to B prime of the vector V, multiply it by the transition matrix P first. So we're just changing bases. We're getting the coordinate vector relative to B of the same vector V. Then multiply that one by A, and we'll get the coordinate vector relative to B of the image of little v. And then we multiply that one by P inverse, and we'll get to the coordinate vector relative to B prime of the image of V. So in other words, we're starting with the coordinate vector relative to B prime of some vector V, multiplying it by P, then multiplying that vector by A, and then multiplying that vector by P inverse, and we get to the same place that we would get if we just multiplied by A prime. So we can see that A prime, multiplication by A prime, is the same as multiplication by P, then A, then P inverse. And so that means that A prime is equal to P inverse times A times P. And that means that A prime is similar to the matrix A. So this is the relationship between similar matrices and composition of linear transformations. Let's look at an example. It says T is a linear transformation from R3 to R3 given by T of the ordered triple XYZ is the ordered triple X, X plus 2Y, X plus Y plus 3Z. And then it says that B prime is this non-standard basis for R3. It's an ordered basis, 1, negative 1, 0, 0, 0, 1, 0, 1, negative 1. And then it says, find the matrix A prime for T relative to B prime. So what we're going to do is we're going to use the fact that A prime is similar to the standard matrix for the linear transformation T. So we're going to use A prime equals P inverse AP, where A is the standard matrix for the same linear transformation. So we have to find the standard matrix A for the linear transformation. Then we have to find the transition matrix P inverse. P will go from B prime to the standard basis B, and then P inverse will be the one that goes from the standard basis to B prime. All right, so how do we find the standard matrix for the transformation? Well, we find the images of the standard basis vectors. So we're going to do T of E1, T of E2, and T of E3. So T of E1 is the ordered triple 1, 1, 1. T of E2 is the ordered triple 0, 2, 1. And T of E3 is the ordered triple 0, 0, 3. That means that the standard matrix A for the linear transformation T, we just line up those three ordered triples as our columns. All right, so now how do we find the transition matrices P and P inverse? So P is the transition matrix from B prime to the standard basis B. And remember, we learned how to get that matrix back in chapter 4. All we have to do is line up the columns of B prime in our matrix. So the columns are 1, negative 1, 0, 0, 0, 1, and 0, 1, negative 1. That's the transition matrix from B prime to B. And then to get P inverse, we can just take the inverse of that. And using technology, I got the matrix 1, 0, 0, 1, 1, 1, 1, 1, 0. So now we're looking for A prime, and A prime is going to be P inverse times A times P. P inverse is this matrix. A is our standard matrix, and P is that matrix. And when I do that multiplication, I get the 3 by 3 matrix 1, 0, 0, 0, 3, 0, 0, 0, 2. Now, notice that the matrix we got, A prime, is a diagonal matrix. That doesn't always happen. And we'll learn in chapter 7 when it does happen. But it's really, really desirable to get a diagonal matrix. So our goal in chapter 7 is to figure out when we can get a diagonal matrix that is similar to the matrix that we have. And what it does is it simplifies a lot of computation if we can use a diagonal matrix instead of a non-diagonal matrix. So let's look at a couple properties of similarity. So the first property says that any square matrix A is similar to itself, because you can always find an invertible matrix P such that A is equal to P inverse AP. The identity matrix is an invertible matrix that'll work. And that property is called reflexivity, or it's the reflexive property. The second property says if A is similar to B, then B is similar to A. So if A is equal to P inverse AP, then there's some invertible matrix Q such that B is equal to Q inverse AQ. And that's called the symmetric property. The third one is if A is similar to B and B is similar to C, then A is similar to C. And that one is called the transitive property or transitivity. Let's just prove one of these properties. Let's prove property 2. So suppose that A is similar to B. That means that there is some P such that A is equal to P inverse BP. Well, if we multiply on the left by P and on the right by P inverse on both sides of the equation, then on the left we get P inverse inverse, or the inverse of P inverse, times A times P inverse. On the right, we get P inverse times B times P inverse. And those two products are just identity matrix. On the left, we have Q inverse AQ, where Q is P inverse. And so this means that B is similar to A. Let's prove a couple of facts about similarity. So suppose that A and B are similar. That means that the determinants are the same. Let's see why that's true. So if A and B are similar, then A is equal to P inverse BP for some invertible P. So that means that the determinant of A is equal to the determinant of P inverse BP. And on the right side, I could write that as the determinant of P inverse times the determinant of B times the determinant of P. And since those are real numbers, that product is commutative. I could just reorder the numbers. And we know that the determinant of P inverse is the reciprocal of the determinant of P. So that product is just 1. So we have the determinant of A is just the same as the determinant of B. And then the last property we're going to prove is if B is similar to A, then B to the K is similar to A to the K. So all of these properties make computation much, much easier. And if we have a diagonal matrix that's similar to the matrix that we have, then these computations are almost trivial. So let's look at what the powers of these matrices look like. So B is similar to A, so B is equal to P inverse AP. So that means that B to the K is P inverse AP to the K. And so on the right side, let's expand that. We get P inverse AP times P inverse AP times P inverse AP dot 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 P inverse AP. And how many factors? There's K factors because we've raised it to the power K. Now, notice the associative property of matrix multiplication allows us to write this as P inverse A times P inverse times A times P inverse dot 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 times P inverse times A times P. And all of these P inverses are just the identity matrix. So now we have P inverse times A times A times A times A times P. And how many A's do we have? Well, we had originally K factors, so there's K A's there. So that's P inverse A to the K times P. So that means that B to the K is similar to A to the K. And that's something we could use if we needed to compute a really large power of a matrix. If we can get our matrix to be similar to a diagonal matrix, then finding the power of a diagonal matrix is really easy. All right, we will see the importance of similarity in Chapter 7. I'll see you in another video.